inviting me to this place. It's a pleasure to be giving this talk here. So let me first acknowledge my collaborators. So I will report several projects, and in all of those projects, Antoine Georges is one of the main players. So the work I will be telling you about is the work I did during my postdoc stay with him. Then there is a long list of other collaborators that also contributed to parts of this project, of what I will be telling you. So what is our task? We would like to understand warm correlated metals, and we would like to say what precise things, or at least correct things, can be said about correlated metal at room temperature and above. And pictorially, we would like to understand the ingredients of the incoherent soup. So the outline of my talk is this. So I will start by motivation. Unlike the previous speakers, especially in the morning session, which gave more general perspective, I will focus more on ruthenates. And so after giving the brief introduction to ruthenates, I will discuss my results first in the single band results, where I will discuss also some of results that were mentioned in the morning sessions on the resilient quasi-particles. Then I will discuss the multi-band situation, so in particular the origin of correlations that are not in ruthenates to be attributed only to the Hubbard term. And then I will discuss entropy and thermopower, and I will argue that it gives a very interesting insight into the degrees of freedom that one has at high temperatures in ruthenate. So ruthenates. Ruthenates do interesting things. The compound I will be mostly discussing is strontium-2-ruthenium-4. It has unconventional superconductivity at low temperature. Other ruthenates do interesting things too. 327 has a metamagnetic quantum critical point, and there was lots of work on nematic properties around that point. Calcium ruthenate is one of the ruthenates that was most stubborn to show its Fermi-liquid nature. So actually all the ruthenates, in all the ruthenates by now, the quantum oscillations were now seen, and quadratic resistivity was seen below a given temperature. And in calcium ruthenium-3, this temperature was quite low, 2 Kelvin. But here we will not be interested in so much in the low temperature regimes, but in the high temperature regime. So you've seen this data earlier today. So the resistivity of strontium-2-ruthenium-4 shoots straight through any criterion you might imagine for the Mott-Riegel limit and shows no intention to saturate. Other ruthenates, the resistivity of other ruthenates as a function of temperature is shown here. For all, the functional dependencies are different, but all share this property of having resistivities larger than the Mott-Riegel limit at large temperatures. So one could say warm ruthenates are bad metals, but what does it mean actually, bad metal? Does Mott-Riegel criterion, in the sense of having KL smaller than, so KFL equal 1, does it have meaning? Are the quasi-particles present? Should one be thinking in terms of quasi-particles at all? So these were the questions we asked ourselves some time ago, and we wanted to address them in a particularly simple setting. So we did dynamical mean field theory calculations on a bath, single orbital bath of semicircular shape. So the density of states of the bath of electrons is described as semicircular. And dynamical mean field theory is a theory which maps correlated bulk problem to a problem of an atom in an effective medium. And we solve this problem with state-of-the-art impurity solvers. So you've seen this slide, this data before. So here is the density of states for this doped Mott insulator. So here U is 4, so the undoped material is Mott insulator. You see a lower Hubbard band, upper Hubbard band, and at low temperatures you also see a quasi-particle peak. On heating up, so different curves are different temperatures, the quasi-particle peak progressively melts, and at high temperatures only the Hubbard satellites remain. It is interesting to follow what resistivity does. So this is doping 20%. This is the green curve here. And one sees that, for instance, in this part where one still sees kind of a hump remaining of the quasi-particle peak, so this temperature is 0.2, one is already approaching the Mott-Rega limit. So one can also look, so K resolve this density of states to get these spectral functions. And you see that at low temperatures, this is the quasi-particle peak and the Hubbard band, lower Hubbard band. And this quasi-particle part of the spectra persists until at high temperatures it merges with the Hubbard band. So that's why we call them resilient, because they are remarkably robust. It is instructive to compare also what is going on with thermodynamic properties. So here, look at the entropy. So the blue symbols are entropy as a function of temperature. You see that, for instance, at the temperature where the quasi-particles were still present, the entropy is of order log 2. So one has already established local moment response, yet some signature of the quasi-particle persists. Let me now comment a bit on the resistivity saturation. So here is a plot of scattering rate, so average over of M sigma over some window given by temperature, so and sigma is self-energy. And you see that this saturates actually, so in this, it saturates much more than the resistivity is due. So the fact that the resistivity is increasing at this temperature is not associated to the increase of the scattering rate. Rather, if one, it's associated, if one uses a Drude description, it is the effective carrier number that is diminishing. So in this sense, bad metal is really like a doped semiconductor controlled by the temperature dependence of carrier number, not scattering. Okay, now I want to go to multi-orbital systems, to realistic systems. So let's now go to this strontium to ruthenium-04. The first thing we need to realize is that these are not doped Mott insulators. So here we are in a situation where the bandwidth is 3eV, so ruthenium is a 4D transition metal. It does not, the interaction elements are smaller. And we are in a situation where U is smaller than the bandwidth. So first thing we need to understand is why, what causes the correlations in the first place. So some time ago, so this is a work from start of my postdoc from 2009. So we simulated this compound within LDA plus DMFT. These are the LDA bands, and we built Vanier functions for T2G states. And this is the interaction matrix that is applied to those, so the atomic interaction. It can be rewritten to a form which is perhaps more intelligible to a human. So one has a term which counts the number of pairs, kind of overall repulsion. And this price is diminished by if the spin or orbital momentum are large. So we use this Hamiltonian fixed value of U to 2.3 eV, a value that we got from constrained RPA ab initio approach. And we then increased J and observed what is going on with our calculations. And we've seen that the mass by J, with J rapidly increases, and that the coherence scales in the sense that I will define in a couple of slides, abruptly drop as the Hundsruhe coupling is increased. So it's the correlations originate in the Sr2RuO4 coupling. And then there was a subsequent work by several groups, notably by Kotliar and Haule, and by Millis and Werner, and also by Luca De Medici, next speaker. And I will just summarize this notion of Hund's method on this slide. So here is a plot of a color map of the quasi-particle weight as a function of the number of electrons and Coulomb interaction. Because we have free orbital system, the maximum number of electrons that we can put in is 6. As one increases interaction at integer filling, the Z drops, and at integer fillings one enters the Mott insulating state, which is depicted by these black bars. And one sees that the first thing one observes is that at half filling, the Mott insulating state occurs at very small interaction strength already. This is one first consequence of the Sr2RuO4 coupling. Namely, if one is at half filling, one is already, the electrons are already at the maximal possible spin. For instance, here, and if so tunneling of electrons will not only pay the price of this Coulomb part, but it will also come with smaller spins. So the price to transfer electrons from site to site is biggest at half filling. And the the opposite occurs away from half filling, where one can actually benefit from the fact that charge excitations have bigger spin and hence lower energy. The other thing is that away from half filling, so the Sr2RuO4 coupling does also something else. It suppresses coherence scale. So here you see very small values of Z, already very far below the actual Mott insulator, whereas at other fillings, the strong correlations occur only in the proximity of the Mott insulator. So here I will add just one more thing. I think very interesting, concise way of explaining what causes strong correlations here was recently proposed by Rutgers group. Namely, if one looks at the effective impurity problem and does the Schrieffer-Wolff transformation to eliminate the charge fluctuations, one gets the Kondo Hamiltonian that contains spin-spin, orbital-orbital, and spin-orbital terms. And it happens that because of strong Sr2RuO4 coupling, when these terms are dominated by virtual fluctuations to half-filled states, then the spin-spin part of the Hamiltonian has suppressed or even ferromagnetic sign due to Sr2RuO4 coupling. And this will have some implications also for what I will discuss later. Now let's return to Strontium 2 ruthenium 04. Let's discuss the crossover into incoherent regime here. Here is a plot of scattering rate divided by temperature as a function of temperature. So quasi-particle scattering rate. One sees that initially the scattering rate follows a quadratic dependence, so after divided by temperature it's a line, and then it saturates, and which means that there is a linear dependence of temperature. And one can use this to identify the coherent regime, and somehow the transition between the two behaviors happens when the gamma scattering rate is of the order of kT, and this can then be used to define the coherence temperature. One can also look at experimental response. So here is the coherence-incoherence crossover seen from the NMR. So this is night shift. Symbols are theory, dots are experiment. And one sees that only at lowest temperatures one sees temperature independence response characteristic of a paramagnetic metal, paramagnetic Fermi liquid. And likewise in the local susceptibility, so as measured experimentally by 1 over T1T. One remark I may add here is here black symbols are also theory, and notice the overall quantitative agreement in real units between experiment and theory. So all the calculations are done for one set of parameters that were chosen so to describe well the mass enhancement as measured by quantum oscillations. And then they are kept fixed also in the later part of the talk. So it's also interesting to look at the photo emission. So what happens, what does ARPES see? This is a measurement. Once heats up, the quasi-particles progressively disappear. These are experiments. This is theory. One sees that in theory they are a bit more robust, so they didn't quite want to disappear. But I think that actually in ARPES it's problematic at these temperatures because the surface is not stable anymore. You see, these are these resilient quasi-particles in a real material context. And if nothing else, what is sure is that the ending of the Fermi liquid regime has nothing to do with the disappearance of quasi-particles. They are around up to higher temperatures. So now I want to go to the last part of my talk, which is the new results that aim to characterize this fully incoherent regime better. And remarkably, this better characterization comes from the measurement, again from the transport measurement, but now thermal response, so measurement of the thermopower or the Seebeck coefficient. So what does Seebeck do in ruthenates? Interestingly, many different compounds that have displayed quite different, that would display quite different resistivities behave remarkably similarly when Seebeck coefficient is looked at. So they start linearly with some, according to Mott law, and then around room temperature there is a plateau that forms, and the value is always about, in the ballpark, around 30 microvolts per Kelvin. So why universal behavior? Already the early measurements suggested that it's associated to entropy. And I would like now to tell you what does mean that the Seebeck coefficient is associated with entropy. So by definition, so Seebeck coefficient is in the linear response defined as a ratio of the current heat current and the current correlation functions. And it's convenient to pull out chemical potential out of the heat, because at high temperatures chemical potential goes linearly, whereas the energy is bound, and hence at the high temperatures this part vanishes. It's a question what is high temperature, but if at sufficiently high temperatures this first part is not important. And when this is the case, the Seebeck coefficient is given by mu over T, and this is by thermodynamic relations equivalent to derivative of entropy with respect to the charge, to the carrier number. And from this point on, one can do two things. One can go to insist on this high temperature limit and evaluate also this mu over T in the atomic limit. This is known under name Heikes formula. Or one can do, for instance, numerical simulation, calculate mu over T, and evaluate Seebeck from that. It turns that a bit better than mu over T works the derivative of mu with respect to T, which is now known under the name of Kelvin formula, proposed by Shastri. This Heikes formula has been found to be successful in several, useful to explain the thermoelectric properties in several localized systems, notably recently on vanadides right next to the Mott transition. But here we have a metal. So are we here expecting such entropic estimates to work? So here we did, so Seebeck in LDA plus DMFT is actually calculated from the bubble, so it simplifies the vertex corrections are not any more there. So there is similar, the input to the calculations are self-energies. And these are the results. So black symbols are theory. Gray line is a simplified calculation of the Seebeck coefficient by this term entropic consideration, so from derivative of mu with respect to T. And the green circles are experiments on strontium to ruthenium-4. And these triangles are for comparison also results for experimental results for strontium-ruthenium-3. So what do we see? First point is that in this calculation, the Seebeck coefficient does follow closely what one would infer from entropy. Okay, so this tells something about the calculation, but does this tell us anything about the material? Well, is there some interesting information about that? To take advantage of the entropic content, one needs to know which degrees of freedom one deals with. And in this respect, it's interesting to look at the susceptibilities. So here is a plot showing the spin susceptibility and orbital susceptibility as a function of temperature. Orbital susceptibility was multiplied by a factor of 10 to be visible on the same plot. So the first lesson is the orbital susceptibilities are much, much, much smaller, and they have a different temperature dependence. Only at high temperatures, both follow, all the susceptibilities follow Curie dependence, whereas as one cools down, the orbital degrees of freedom get quenched, and only the spin degrees of freedom remain, follow the Curie law, and those spin degrees of freedom only at lowest temperature start to go to a saturated Pauli response. And here you will find a connection to what I was describing earlier. So the fact revealed by work from Rutgers, and actually also it was there is also a Japanese paper from Okada from '73 that has already described that the orbital Kondo temperature will be much, much higher than the spin Kondo temperature in this respect. So we also calculated entropy as a function of temperature by a trick, so this should be looked as an estimate. So what does entropy do as a function of temperature? That's plotted here, and these lines are a value which is for, so here we have 4 electrons in 3 orbitals, so the ground state multiplet, atomic multiplet is that of the spin 1 and orbital moment equal to 1. And but when we reach room temperature, the amount of entropy that is released is log free, and by 1000 Kelvin, one has full entropy of the log free from spin and log free from orbital moment. At his, well, it's liberate this entropy. And now we know the degrees of freedom that are being available, that are, so for instance, at room temperature, there are just spins and not, no orbital moments. And one can apply Heikes analysis. So this is analysis, this is an estimate of the thermopower just from an atom with the degeneracies appropriate for having spin degrees only. And by doing this calculation, one gets a value of 30 microvolts per Kelvin. That is this dotted line. And so in this sense, the Seebeck coefficient, so the fact that in ruthenates around room temperature have Seebeck coefficient of 30 microvolts per Kelvin about is pointing directly to the presence of spin degrees of freedom only. And as you heat up, the thermopower goes down because also the orbital moments appear, and then this the same calculation will give actually negative result. So how am I doing with time, Nigel? 6 minutes, that's great. So what about, can one expect such considerations to work universally? Is it always, so one will just measure thermopower, and when one will see a plateau at a given value, will it be useful to infer the degrees of freedom? Well, answer is no. Actually, already in this material, if you look around in a different direction, you see different response. So this is theoretical prediction of the C-axis Seebeck coefficient in same material, just in different direction. and one sees that it shoots straight up and it has no intention to saturate. So why does it do this? So to understand when do the entropic arguments apply, it is best to first consider the simplest possible example. So let's take the non-interacting electrons. And let's consider d mu over dt for these non-interacting electrons. So this is what d mu dt is, and this is what Seebeck coefficient is, except for the fact that here, for some reason, I don't know why I use here epsilon, here omega. One sees that the two expressions are very much the same, with and the only difference is that here the transport function, which includes also information about velocities, about dispersions, takes the role of the density of states in this formula. So when the transport function and the density of states are very different, and this can be, one cannot expect those two expressions to give the same result already at the non-interacting level. So let's look at the transport functions for our ruthenates. The blue, so the solid lines are no. So how is actually the code? So these the curve centered here are the AB transport functions, and these are the C-axis transport functions. And one sees remarkably different behavior. So the C-axis transport functions have a peak that is centered at negative energies, and this peak is there already at the non-interacting level. So where does this peak come from? Why is it so different? So the C-axis transport is controlled. So this is a body-centered tetragonal material. So the C-axis transport is dominated by hopping of this guy to that guy in the center of the zone. And in a tight binding picture, it comes with a term. So the C-axis, so one can write epsilon as energy as a function of some in-plane part plus this that gives hopping in the z direction. And one sees that the dominant contribution to the kz, to the tunneling in the z direction comes for small in-plane momentum. Here it should be x, not kk. So for small in-plane momentum. For instance, if I plot epsilon of k, here is a plot of epsilon along some part of the in-plane, so this is in-plane momentum, and I plot this energy for kz equal to 0 and kz equal to pi. One sees that at negative energies, the difference between the two is maximal. Or if one plots this tunneling matrix element along z direction as a function of the in-plane Brion zone, one sees this bright peak. So mostly to the tunneling in the z direction, only the states that are far below the Fermi surface contribute, and this gives rise to a whole, we call this a whole filtering mechanism. So now let me go to conclusions. So I discussed a bit resilient quasi-particles. I insist on the fact that they vanish around the Mott-Joffre limit, and that the state above this temperature is more closer to an insulator than to a metal. And earlier we've heard a very interesting idea by Vlad that actually puts this on quite firm grounds. And I encourage you all to go also to look at Yaksha's poster at the poster section. Then I looked at the multi-orbital systems at ruthenates, and I've first the origin of correlations there is different, so they come from the Hundsruhe coupling, and that this Hundsruhe coupling changes the game qualitatively in the sense that the incoherent state now has two distinct stages, and in the first part of the crossover, just the spin degrees of freedom are being released, and in the second part also the orbital degrees are being released, and I have discussed how this is seen in the Seebeck coefficient. So thank you. Oops, no. Okay, these are things that, thank you.